Okay, so let's discuss a question from theory of machine. So we are given with a disk and springs are attached to it as shown in the figure. So we need to find out the small angular oscillations of this. Now the disk is at the center, it is fixed, so it can only rotate about the center. The center cannot translate. It can only undergo fixed axis rotation about the center. And so what we need to do is, just like in any natural vibrations problem, what we do is we give an angle, we rotate this, like this is the initial position, okay, and so we rotate this with angle theta. So when I rotate with the angle theta, this is this line which was initially like this, now it's slightly inclined. So because of the slight incline, now the spring will be acting in this way, okay, and the spring will be acting in this way. So the force is nothing but, the spring force is nothing but kx. So kx is something which let me draw a vertical here, okay, this movement is x, okay, the spring movement at the top as well as the end at the bottom. So at the top the spring is stretched, at the bottom also the spring is stretched by angle x. So whenever the spring is stretched, okay, it tries to come back to its initial stretch, so it tries to pull, okay, and if it is compressed, it tries to push. So here in both the cases the spring is in tension, it is stretched, so it tries to pull back. So that is kx. So kx is the force acting. Now the mass and all are acting at the center mass of the disk, okay. So this is the center, the mass of the disk will be acting at the center, okay. So now there is an unbalance of force, and this unbalance of force produces acceleration, and this acceleration, if it is in the form of omega square x, it will lead to simple harmonic motion. So that is the thing. So initially this is the equilibrium position, and now here is something which we have moved it, rotated it by angle theta, okay. So at this position, when we have rotated by angle theta, at this position the moment about the center, now remember that just like sigma f is me, summation of moment about any point or about the center, it should be I alpha, where I is the mass moment of inertia about the center into alpha. So this is a synonymous equation with F is equal to ma, but we use this equation when you have a rotational unbalance of forces or unbalance of moments. So then we can use to get the angular acceleration. So let's do it in the same way. So moment about C. So moment about C, the kx is towards left and it produces, so we take positive moment because we have rotated angle theta in a clockwise, so we take clockwise moments positive, because we assume that theta is like this and theta dot, which is omega, is also like this, theta double dot, which is nothing but alpha, is also like this. So we take this clockwise direction as a positive, and then we apply the moments. So kx is towards left side, so kx produces an anti-clockwise movement, which is nothing but force into radius, that is the lever, the r moment arm is the radius, so kx into r is then moment, anti-clockwise moment produced by the left spring. Now the right spring also produces anti-clockwise moment, the kx is like this, so it tries to move anti-clockwise about x, so kx into r. So this is the only moment acting because of the springs at the center, and I alpha is nothing but the rotational inertia. So now effectively what we get minus kx into r 2 times because of 2. IC is the mass moment of inertia, this is the disk, so mass moment of inertia about the center is mr square by 2. Remember 2 is very important, it's not mr square, mr square would be for the ring. So this is mr square about 2 for the disk. Now x can be expressed, x is a small motion of the perimeter point. So when you have a disk rotating by a small angle because it's small oscillation, so this moves like this, and the x is nothing but, there's a small motion of the any peripheral point moves as x is equal to r theta, and because it is small, so we can assume that it's a horizontal, okay. So x is equal to r theta is for small, we can write. So minus k r theta, this is nothing but r square theta into 2. And what is alpha? Alpha is derivative of angular velocity, and angular velocity we know it's theta dot. Angular velocity is again change in angle per respect to time. So alpha I can write omega dot. Omega is nothing but theta dot, so it's theta double dot, right? So this can be written as minus 2k r square theta is equal to m by 2. So m r square into alpha. So r square alpha is theta dot. So this entire thing we can write in this way: minus 4k by m theta is equal to theta dot. So this is just in like the rotational equation. So let me write it here. So how are we getting? Theta dot is nothing but minus 4k by m theta. So this is just synonyms. So this is a relationship in rotational coordinates. So but if you compare with our natural vibration equation, so x dot is minus omega n square into x. So x is the degree of freedom there, and if your acceleration or the double derivative of x varies as minus omega n square into x, then we get simple harmonic motion. The body oscillates in simple harmonic motion with the frequency of omega n. So comparing with in that form, this 4k by n, m has to be omega n whole square. Okay, so comparing, because we got theta double dot as some constant into theta. So when you have this kind of equation, you get simple harmonic motion, and that constant is nothing but 4k by m, and that is the square of natural frequency. So root 4k by m is natural frequency. So answer is B. So when you have any kind of these kind of problems where you are given with the situation and you want to find out the natural frequency of vibration, you have to write down you have to first decide whether you want to, it's a linear system or a rotational system. Now that we have decided, because the disk is something which can only rotate. So you have to apply the rotational, displace it by theta and apply the rotational equation of motion and try to express the degree of freedom here is theta. So try to express double theta dot, the time double derivative of theta dot with theta. So in something in this form, theta double dot is some constant into theta. So that constant, once you get an equation in this form, it means that it's a simple harmonic motion, and then that constant will give you the natural frequency. So 4k by m. Thank you.